Hi, everybody, and welcome to this session of Astronomy 120. This is the Thursday session, and today we're continuing basically what we started this week. So we're going to finish basically Unit 12. And if you don't remember, basically Unit 11 is just a reminder, dealt with with how astronomy basically evolved, the different models basically evolved, and how we came up with the understanding, or at least we evolved from the so-called geocentric model towards the heliocentric model, where the solar system, those wandering objects, the objects that move in the sky, they're actually moving around the sun, okay, not the Earth. And that was really a big, if you wish, change in reference frame. Basically, we used to think that everything revolves around the Earth, and now all of a sudden the Earth is not the center of the solar system, at least. Okay, this later on laid the foundation for more studies of the solar system, and led to, as I said last time, basically to Mr. Kepler basically finding his 3 laws. And this is where the Unit 12 comes into play. Okay, actually, we're going to go a step beyond what Mr. Kepler has found, and we're going to discuss actually what Mr. Newton did, because it's interesting that Mr. Newton, there are a lot of ants, and I'm here in the office, by the way, and there are a lot of ants in here. So that's what I'm trying to get rid of. Anyway, the point being in here is we are going to go a step beyond Mr. Kepler and try to explain what those laws are. Kepler's laws are based on experiment. They're empirical laws based on observation, okay? And then Mr. Newton came up with an explanation for those laws. He went a step beyond that. He went a step further than that. He actually explained what this experimental laws were. And then based on his laws, based on his explanations, based on his model, which is a theory now, we made some predictions. And among other things, basically Halley's Comet, and also the different moons of Jupiter, and that gave us a mass for Jupiter, and so on and so forth. There are a lot of things that Newton's laws were able to help us do. As I discussed last time, Newton's laws have limitations. And it was later on when Mr. Einstein basically came up with a better explanation for a lot of these things, okay? With actually a more advanced, if you wish, theory. Which begs to answer the following question: is Mr. Einstein's theory the ultimate theory? Is this the one that answers all of the questions? Obviously, it's not. The reason why I'm saying that is because modern physics continue to evolve, and now we know it also has some limitations. Until now, nobody was able to come up with the better, if you wish, the one that succeeds it, the one that comes after that, but we can't. We don't have the, we were not successful up to this point. We know it has limitations, okay? And that is basically how science progresses. That's how all of knowledge is progressing. You make an observation. Based on that observation, you came up with theory or a model, hypothesis, then you test it. And if it tests, then you test it again. And if it tests and tests it time and time again, it becomes a law. So law is really an experiment that can be tested, and that has been tested, and always when it's tested, it yields the same result. That's what the law in science is. That's what the law in astronomy is, okay? Hold on. Okay, so that's basically in a nutshell what we're doing in here. I'm in the lab in here. Hold on, guys. Okay. Again, basically, as I was saying, basically, that's how science progresses. You always have to make a prediction based on the current model, and then it becomes a law. And again, that's the point that we're trying to take from this whole thing. In addition to the value of Kepler's laws, Kepler's laws have an inherent value in them because they will help us understand a lot of things that are of how the solar system works. Okay. And you guys have homework problems. You should be able to, hopefully you guys have no difficulty with them. One of you guys sent me a message. I don't know if it's in this class or the other class, that a general question about the homework. Basically, I already posted a recording from last week on the homework, at least the 2 sets. Okay, and I did not do it for the third homework because I believe it's also straightforward. But if you guys still think that it's something useful to have some sort of a discussion about it, I'll be more than happy to also do that too for the third homework. The point of this homework problems is not to challenge you. That's why I'm doing actually a recording sessions for them in detail. It's actually for you guys to do them because I believe in their value, in a sense that if you do them and you do them successfully and you understand the different steps in them, that should empower you even further to understand better the topic, to really understand where these things are. So these 3 laws that we're going to discuss today are part of that process, and they are, one of them is more or less qualitative law, but the other 2 are actually quantitative in a sense, especially the last one. We're going to do some examples with it, and you will see the value of how you come up with numbers and what they mean. Okay. So let me share with you the screen. So again, these are the objectives from this unit, unit 12. So identify the contributions of Mr. Tycho Brahe, Kepler, and Galileo, okay, to astronomy. Describe the properties of ellipses and how they relate to planetary orbits, and list Kepler's 3 laws. And carry out calculations. We're going to do some calculations based on at least we take some examples when we do those, and discuss why Galileo's first telescopes were so revolutionary. Okay. Let me probably start with the last point in here to talk about it. Remember, Mr. Copernicus came up with the idea that the sun is the one that is in the center of the solar system, and all the planets revolve around it, including the Earth. However, he also subscribed to the idea that the path must be perfect circular paths because, again, the heavens are perfect. They're devoid of men's basically sin. That's why, and the heavens are perfect. So everything has to be perfect. And the only thing that is perfect in the terms of geometry is a circle, because it has perfect symmetry. So that was really the argument, and there was nothing to contradict that, because how can you go wrong with that? I mean, you have to have really some sort of a force to cause an object to go in a zigzag pattern, to change its path. So, but in a circle, you really don't need that. You don't need an external force as long as it's going in a circle, so it should be fine, okay? Obviously, if you would want to carry out the experiment, and this was well known even at that time, if you would want to maintain a rock to go in a circle, you have to really tether it to a string and then spin it. So everybody knew then there must be a force to cause all of these objects to stay, because that's the force of the string for the case of the rock, to cause these objects to remain in this circular path. So that is the idea behind it, and those circular paths. Then Mr. Kepler came in later on and analyzed the data of Tycho Brahe. Tycho Brahe basically made all kinds of observations. He did observation night in, night out, actually, in a private island in near what is it, Denmark, and he basically he was doing observations on a regular basis, basically tracking the positions of the planets, Mars, day in, day out, every night, okay, throughout the year, many years. Same thing for Venus, the same thing for Mercury, the same thing for Jupiter, the same thing for Saturn, the moon, the sun. He collected a lot of data, okay, a lot of data. Then Mr. Kepler took those data, and the first thing he had to get rid of is those circular paths. Because when he looked at the data and when he analyzed it, they don't make sense. It does not make sense that the paths could be circular, but rather they were elliptical, more so for others than some, okay? But they are elliptical nonetheless. So that is basically the first law of Kepler. really. So Kepler's really contribution to this thing in here, he took the data and he analyzed it. And since he had a lot of math background, he was able to come up with an interpretation of that data, because part of the objectives in science is to be able to interpret data. And that's exactly what he did. He was able to analyze that data and interpret it. So the first thing that he deduced from that data is the fact that the paths are not circular, but rather they are elliptical. And then Mr. Galileo, like I said, he took a telescope, a toy at that time that existed at the time. It was, I don't know who invented it, so it's not really him who invented it, somebody else. But the point being, he took a toy and he modified it a little and he pointed towards the stars. The first thing he noted was, among other things, is that the moon is not as smooth as it appears to the naked eye. It has also hills, it has valleys, it has mountains, if you wish, it has cracks in it. It's not really as perfect as you might think. So that throws away the idea that the heavens are perfect, because here is, look at it with your own eye. And this is something in the heavens. Shouldn't it be perfect like everything else? And you're telling me the reason why we have mountains on Earth and we have valleys and we have all of these things is because of basically what man has done on Earth and sinned, and therefore, so that hypothesis does not hold water anymore. That is one thing. The other thing that he did also, he noted on Jupiter, the first night, that there were 3 objects orbiting it. The next night, he noted a 4th object orbiting it. And he was able to track them down. Those are moons of Jupiter. Those are outside of Earth. So the idea that everything must revolve around the Earth here is completely disproven by the work of Mr. Galileo, because you can look at Jupiter and see 4 moons revolving around it. So at least these 4 moons do not revolve around the Earth. They revolve instead around Jupiter. So you see here, this whole belief that the Earth is the center of the system, the solar system, and all of that has been disproven just by the work of Mr. Galileo, just by looking at these things. Mr. Galileo did other contributions, actually, not just this. He was able to find the value of G, the universal acceleration on Earth, which is a value of 9.8. He was able also to quantify and come up with a way of measuring velocity and measuring acceleration, and he came up with all kinds of key concepts. The concept of inertia, which is critical. If you take a rock, for example, and if you throw it in one direction, if it's not in the force of gravity or any object, it should stay in that direction all the time. So the only reason why the planets are going around the sun is because of the fact that they are subject to a force, which is in this case the force of gravitation. So this is the work of Mr. Galileo and the work of all of these people put together, okay? So Galileo at the end, because of the fact that he believed in the work of Copernicus, he was prosecuted by the church for his belief, because of the fact that the church subscribed to the idea at that time that the Earth is the center of the solar system, the sun revolves around the Earth, and the Earth is actually is not, as you're telling us, is not round, it's flat. There are all kinds of beliefs at that time, and that contradicted with the church teachings, and he contradicted with them. Okay, so he was actually prosecuted and put in house arrest until he died, because of that, because of this, his work and his belief and everything. Actually, the church banned his publications and books, and it was until like 1996 or something when finally the church, because he was excommunicated from the church. So he was basically until 1996 when the Pope basically recognized that was not correct, and basically admitted the mistake of the church. So just to give you an idea of how sometimes culture and what society believes sometimes contradict with science too. This is not true only for the church, it's true for all kinds of nonsense beliefs out there. Anyway, So the point being in here is that the other thing also that he noted is the sunspots on the sun and the craters on the moon and the Jupiter moons and all of those contributions. So Mr. Galileo did a lot of contributions in here. The 4 moons of Jupiter now are known by his name. They are called the Galilean system. The 4 moons of Jupiter, again, from proximity up to Jupiter are, you have Io, you have Europa, you have Ganymede, and you have Callisto. Those are the 4 moons of Jupiter. One of them, Ganymede, is bigger than even planet Mercury. So those are big moons. All 4 of them are extremely big. Callisto and Ganymede are super big moons. They're bigger than Earth's moon, and even Io is bigger than Earth's moon. So 3 of them are bigger than that of the Earth. And the only one that comes close to these 4 moons actually in size, or actually that compares to them in terms of size, is actually the moon of Titan, the moon Titan of Saturn. Titan actually the 2nd moon in the solar system, and it too is bigger than the planet Mercury. So there are 2 moons in the solar system that are bigger than the planet Mercury. Callisto is slightly less than Mercury. So just to give you an idea, that Mercury, I mean, this moons can be very big, and so is Earth's moon. Earth's moon is actually, relatively speaking, big. It's actually what, the 5th moon in the solar system, or is it the 5th moon? I think we have what, Ganymede, Titan, Callisto, Io, and then Earth's moon. So it's the 5th moon in the solar system in terms of size. So it comes ahead of Europa, which is the 4th moon of Jupiter. So again, he discovered these moons using that telescope, and now that, without a doubt, proves the idea that the solar system does not revolve around the Earth, because here are 4 objects that revolve around the sun, around Jupiter. Okay. Here is his notes actually. Okay, so this is his drawing of the moon. Okay, and what he noted, and this is actually the different moons of Jupiter and how they revolve around it. When he looked at Saturn, he was puzzled by it. And his drawing, it looks like it's like Mickey Mouse basically nowadays, because it's like a spherical object with 2 ears around it, because he didn't understand what those two things around it. It turns out that they were rings. You had to wait until Cassini later on when he basically recognized that those are actually disks going around the planet. But he did a lot of contributions in here in terms of observations and in terms of data and in terms of things like that. Okay. So again, he also studied Venus, as I was saying. Okay, and he noted, among other things, that Venus goes around through phases just like the moon does. Okay. So when you look at Venus, it's not always the same brightness. It dims sometimes and it brightens some other times, depending on which phase it is. So those are some of the contributions of Mr. Galileo into this thing in here. And I decided, like I said, I thought that this is actually a very important topic that we have to start with him because of his major contributions into this field in here. Anyway, as I was saying, Tycho Brahe came in later on and he collected a lot of data for us. Okay. And he didn't have a telescope, as you can see from this depiction of him looking at the objects in the sky and measuring their angles, okay, and how much they are. So he had some conclusions based on the parallax that he couldn't reconcile with it, and that is, remember, from Aristarchus calculations, basically, and estimates for the size of the sun and the earth and the moon and the distances and things like that, where he concluded that the sun does not revolve around the earth, but the other way around, that the earth, because it's smaller in size, must revolve around the sun. Tycho Brahe basically concluded, basically he had like a 50-50 thing, in a sense, like he had a compromise. He was under the, according to his observation, all of the planets, especially the closer ones, they revolve around the sun. There is no question about it. But because he couldn't find that parallax, Remember, he didn't have a telescope. He was using, although a precise instrument in here that can detect an arc minute, but an arc minute turned out to be a very, very big angle for the parallax. Parallax is a fraction of an arc second, so it's not even for the close by stars. So his precision devices could not detect that. Okay, he witnessed the supernovae because of the fact that he was doing continuous observations. Again, it's his work. And later on, he hired actually Kepler to work with him on the data. He was kind of, he protected the data. He didn't want to have Mr. Kepler all the data to himself because he thought he's not going to get at least the recognition he deserves. And Mr. Kepler did not have access to all of the data until Mr. Tycho Brahe passed away. Then at that point, he took the data and he started analyzing it. And the first conclusion, as I was saying, is the fact that the path of the planet is not a circular path, but rather it's an elliptical path. So what is an ellipse? An ellipse has 2 points called the focal points. An ellipse is the assembly or all of the points that are at an equal distance from these 2 points. If you take a string and wrap it around those two loose string, wrap it around those any 2 points, doesn't matter which, as long as it's loose enough, and take a pencil and draw it and go around completely 360 degrees, you draw an ellipse. So what is the distance between this point and any point? It's the sum of this 2 strings minus, it's the length of the entire wrapped string minus the distance between the 2 focal points. That's all. Okay. So that is what an ellipse is. An ellipse is characterized by this big elongation. In this case, it's called the distance from end to end is called the major axis. Half of the major axis is called the semi-major axis. And the flattened portion in here, the distance from the flattened portion up to the other side, to the opposite side, that is called the minor axis, depicted in here by the green line, dotted line. That is the minor axis. Half of that is the semi-minor axis. The distance, the A in this case, is the semi-major axis. Remember this number, okay? Semi-major axis is a very important number that you're going to use in your calculations. It usually uses the letter A for it. The semi-major axis uses the letter B for it. The distance from the focal point to the center is the focal point, the focal distance, which is the symbol for it usually is the letter C. Okay. The eccentricity is by definition this ratio of the focal distance over the semi-major axis. If we're dealing with a circle is actually a special case of an ellipse, where its center, the center of the circle, is when the 2 focal points collapse on each other. So in other words, the distance between a focal point and a focal point in the case of a circle is 0. And the focal point are actually the center in that case. So the focal distance is 0. So the eccentricity of a circle is exactly 0, meaning that this distance, the focal distance, is 0 divided by the radius of the circle in this case, because it doesn't matter. The semi-major axis is the same as the semi-minor axis in the case of the circle. So the circle is a special case of an ellipse. Only difference is the eccentricity for it is exactly 0. That's all. So a circle, if we find an eccentricity, and it's a very important thing to look at when you're looking at astronomical data, is to look for the eccentricity of the object, of the path of the object, and see how far off is it from a circle. It is circular if it's exactly 0, and if it's close from 0, it is very close from a circular motion, but not quite. How far off is it from 0? That will tell you how much eccentric that ellipse is. The maximum value for the eccentricity is 1. Why is it? Because if I take the focal point and move it all the way, think about this ellipse is going to collapse on itself. It becomes a line, basically. In other words, the distance of the semi-major and minor axis becomes 0 at that point, and the entire ellipse will be just like a flattened line, where the focal distance will fall exactly on where the semi-major axis is. In other words, the ratio of that distance over the other distance is exactly 1. So this is the maximum ellipse that you're going to have, is 1. Actually, maximum 1, it doesn't make sense for planetary motion. Honestly, why? Because that means the planet or the object will fall right through the sun. Yes, it's its maximum, and it's when it's far away from the sun. But then it's going to travel and travel. Since it has no semi-minor axis, it's going to go through the sun. In this case, it's going to be captured. So having an eccentricity of 1 doesn't make sense in orbital mechanics, in astronomy. But just to give you the mathematical difference between the two, at one extreme, the eccentricity is 0 for a circle. At the other extreme, the mathematical value for the eccentricity can potentially be 1. Practically, it cannot, but it can be a big number. Meaning, what I mean by big number, bigger than 0, close from 1. It can be 0.8 if you like. That means a very highly elongated path, like Sedna, for example. Sedna has a very highly elongated elliptical path. So the eccentricity now is a quantification. So again, here is different different elliptical paths in this representation in here, where the eccentricity goes from 0 for the case of the planet in the blue, which is a circular path, to a slightly elliptical path for the second one, to a highly elliptical path, to a highly elongated path for the last one in the picture in here. Okay, so the eccentricity is really a measure of how stretched the path is. Since all of the planets move in orbit, move in elliptical paths, then that is basically, some of them will have a high eccentricity, like in this elongated shape, and some of them will have very low eccentricity, as a matter of fact, very close from 0. Not quite, but very close from 0 from circular path. So this is basically how orbits are. And this is extremely different from what Mr. Copernicus has thought, especially for the case of Mars. Mars has, relatively speaking, a high eccentricity. So that went off completely, and that's why it causes a lot of headache for the astronomers in the old days. The Earth apparently has a relatively small eccentricity, so its path, think about it this way. The Earth can be as close as from the sun as 147 million kilometers, and as far from the sun as 153 million kilometers, or something like that. So on average, it's about 150 million kilometers, and it goes 3 million kilometers in and 3 million kilometers out. 6 million kilometers is a lot, by the way. 6 million kilometers is a lot. From the Earth to the moon, it's only 384,000 kilometers. So take that distance and multiply it by 3, and multiply it by 6 more times to see how much it is. I mean, the distance from the Earth to where James Webb is what 1.5 million kilometers. So it's 4 times the distance from here to the James Webb. So that's how much the Earth deviates in and out. But that's nothing compared to 150 million. 6 million is nothing compared to. So most of the time, the Earth is basically almost in a circular path. So that's just to give you an idea of what's going on in here. Again, his first law basically states that the planets move in elliptical paths around the sun. And the sun sits in one of its focal points. So remember, an ellipse has 2 focal points. The sun sits in one of them. It doesn't matter which. Pick and choose. At some point, the planet will be close from one focal point, and the other times, 6 months later or half a year later, is going to be in the opposite direction, closer from the other focal point, far away from the first one. So the sun sits in one of the focal points. This is an exaggeration. This picture is highly exaggerated. The sun is so big. And these paths are, at least for the most of the planets, are extremely close from circular paths. They're not exactly circular paths, but close enough. The two focal points actually are inside the sun. The two focal points are exactly inside the sun. And even the sun itself, if you have a highly precise device, wobbles a little bit in its path. So if the planets, all of the planets line up on this side, the sun is actually on the other side of that wobble. But because its mass is so big, if you take all of the planets and all of the objects in the solar system and put them together, the sun represents 99.98 of everything. So it's basically, the others are negligible. That's why its wobble is not detectable, at least with the low precision devices. So you really have to have a very high precision devices to see that. But the point being in here is that the sun sits in one of those two focal points as far as the planet is concerned, and the planet is going in an elliptical path. At some point, it's close from the planet, from the sun. This is called the perihelion. This is this distance when it's close by. When it's further on the opposite side, it's called the aphelion, on the opposite side, basically, the opposite. On these two sides in here, those are the equinoxes when it's on this side. When it's in this toward one of the semi-major axes one way, or this other semi-major axis in the other direction. All of this observation was useful actually and helpful to understanding orbital mechanics. Man, there's a lot of ants in here. I'm sorry, guys. Okay, been trying to get them. Hopefully they don't go into my ear. This is the lab, by the way. Okay. Somebody must have had lunch in here. Anyway, the second law of Kepler states that the planets, as they orbit the sun, they sweep equal areas at equal amounts of time. Let me give you an example. Let's say, for example, this span of time is 2 months. And you take an imaginary line and you connect it between the sun to the planet. And that line, which is an imaginary, not a real line, is going to sweep this arc. It's going to move this arc in 2 months. You measure this area, the one that is shaded in here. Now you wait 2 more months. It doesn't matter where really, but if you like, you can do it on the opposite side when the planet is nearby the sun. Okay, and you wait for 2 months after that. Well, the imaginary arc, the imaginary distance, I'm sorry, the imaginary line is going to sweep this area, meaning it's going to, the planet will travel through this arc, so that this area now is the one that is swept in 2 months. If you measure these two areas, this area and this area, they're the same area. Meaning that somehow the planet is moving slower when it's further away from the sun, and it's moving super fast when it's moving close from the sun. This is because it covers a bigger arc in 2 months in this case, whereas it covers a small arc in this case in here. Remember, the radius compensates for that short distance, if you wish, in the arc in here, because you have a bigger radius, bigger distance in this case. So this is basically how the second law is. Both of these two laws are related to something which is extremely important, and it's known in physics actually as angular momentum. Because when the solar system formed, there was no external torques after that. So somehow, because of the force of gravity, all of we're going to come back to this point in here how the solar system formed. So all of the different pieces, the gases and the different basically rocks and the different, they start to come together. As they come together, they speed up, they gain speed. That's what's going on in here in terms at least of the sun and how it formed and get all of that temperature. But the objects that are closer by, they move faster, and the objects that are further away, they move slower. And that is actually a conservation of angular momentum. Not only that, but also that explains the ecliptic path also of these planets. They are all more or less on the same path because of the fact, or at least the same plane, I should say, because of the fact that the angular momentum is actually a vector, not a scalar, not a number. It has direction, meaning not only its magnitude is conserved, and its magnitude has to do with this speed being high close from the sun and less away from the sun, but its direction is the same for all of them, and the direction is given by what is known as the right-hand rule. So if you take the palm of your hand and you curve it around, the direction of the angular momentum in this case is perpendicular to this curling. This is the right-hand rule. And that's exactly what's going on in this case. So all of them have the same direction, so they're all curling in the same way, in the same place. So that's how all of the planets basically happen to be on the same plane. Unless something happened to them later on, like for example, with a collision with a different object in the solar system or another planet, or they were yanked by a planet or something like that from their path, then they deviate a little in and out, especially for the objects that are in the Oort cloud far away from the Earth. They brush against the interstellar space, and sometimes stars, because the sun is actually not stationary, moving around the galaxy, sometimes they interact with the stars nearby and they get their path disturbed. Okay, so unless of these interactions, then that's how the solar system formed, and it has to do with what I was saying, the angular momentum. If you don't understand the angular momentum, think about the ballerina, the lady who dances basically on ice. If she brings her hand closer to her body, she speeds up as she's spinning. Okay, if she opens up her hand, that's how she slows down, and that's exactly what you do also on the merry-go-round. Okay. So if you want to slow down, all you have to do is move outside, or at least open, basically, it's going to slow you down. You get more, in this case, moment of inertia that's going to slow you down. Anyway, so this is the third law. The third law, actually, it took him a little bit more time to come up with it because it needed a little bit more work. And it was not obvious immediately. That's why I was telling you earlier about the A, the semi-major axis, that it plays a major role, is because of the third law of Kepler. So in this case, is the third law is you take P in years, the time it takes for the planet to go once around its orbit. If you start counting from January, wait until January of next year, basically. That's what P is. Full year for Earth, full year for Venus, but Venus's year, not Earth's year. Okay, full year for Saturn, and again for Saturn, not Earth. Okay, in Earth years. How many years on Saturn? In Earth years, not in days, not in minutes, not in seconds, in Earth years. That's what the formula is equal to A cubed. A cubed is the semi-major axis in astronomical units. Again, it's the semi-major axis, not the semi-minor axis. It's the semi-major axis, the distance between the center of symmetry, not from the planet, not from the sun, I'm sorry, but from the center of symmetry toward the planet. When it's either its maximum or its minimum distance, but it's from the center. For the case of, or what you can say is you take this distance, which is this whole thing, major axis, and divide it by 2. Which is in a sense adding the overall distance when it's in its far away distance from the sun, plus the distance when it's very close from the sun, and divide that. In other words, the average value between the perihelion and also the aphelion. Okay, so that's really what this value is for A. It's a semi-major axis. It's halfway. It's the average value of the two. For the case of the Earth, it's 150 million kilometers, or 1 astronomical unit. Okay, but this formula in here has to be very, very careful with it. This formula works only when P is in years and A is in astronomical units. If P is in seconds and A is in kilometers or meters, then you need a number in here to fix the units. You need a constant to fix the units. So this is basically the third law of Kepler. I promised to talk a little bit about Newton, and it's very important that we talk about him too, because he took these three laws and he explained them a little bit better. Okay, he came up with his own law. Okay, and it's going to be coming handy down the road too. So here is the story. Basically, after London was hit by the plague at that time, similar to our current conditions, basically, where we have the corona basically sent most of us home. In his time, it was actually the plague that hit London, and everybody was sent home to go to basically, what do you call it, isolate, okay? At that time, so he went to the countryside and he was approached by, I forgot his name right now, but he was given, look, you came up with three laws of motion, because Mr. Newton at that time, he had three laws of motion, and the three laws have nothing to do with these laws. They are, the first one is the law of inertia, which is really the work of Mr. Galileo, but he just basically put it, he took his words and basically put them in the fact that if an object is not acted upon by an external force, it's going to stay in its path with the same speed. It's not going to change direction. The second law says basically that if an object is acted on by a force, then it's going to accelerate, and the acceleration is inversely proportional to the inertia, but it's proportional to the force also. And the third law states basically that the if two objects interact, they interact in such a way that if one exerts a force on one, the other one exerts a force that is equal in magnitude and opposite in direction. That's called the action-reaction principle. Now, these are the three laws of Newton. But then he was handed these three laws of Kepler and he said, can you explain these three laws that govern the objects in the sky based on your three laws of motion? That's the task he has before him. So the first thing he needed to do is find a force that causes the planets to go around the sun. That's his biggest challenge initially. And it did not take him too long, honestly, to come up with that law. All he did was he compared he said, forget about the planets around the sun. I'm going to focus only on the moon around the Earth. And I believe if I find that answer, I can tell you exactly what causes the planets to go around the sun. It must be the same law, except I have to sub, instead of the moon, I have to sub the planet that you were talking about. And instead of the Earth, in that case, I have to sub it by the sun, and we're done with it. That's his reasoning. So he needed that force, and he based it first on the moon. He said, okay, the moon is actually going around the Earth, and what causes to go around the Earth must be the same force that causes the apple to fall on the Earth. Because if you take an apple and you drop it, it's going to fall to the ground. So he reasoned that these two must be related. He knows how much the apple falls to the ground. He knows G, the value of the universal acceleration. That was actually computed by Big G himself, by Mr. Galileo. That's why we call him Big G, because of his contributions in science. Okay, anyway, so he has the value of the universal gravitational constant, well, not the universal, I'm sorry, it's a gravitational acceleration, which had the symbol G, by the way, little g. And that was measured by Galileo himself to be 9.8 meters per second, and that's how much an apple will fall to the ground. The moon is not on the ground, though. It's far away from the Earth, and at that time, there was an estimate for its distance. Remember the calculation of Mr. Aristarchus, and also of, I lost the name for it, right? But we had actually distance for the Earth to the moon. So we know how much the moon is, 384,000 kilometers at that time, okay? And we know how long it takes for the moon to go around the Earth, 27.3 days, to be more specific. That's the revolution of the moon around the Earth. That's the sidereal lunar month, okay? And so those are all facts. So from here, he can find, using mechanics, he can find the acceleration of the moon. And he knows the distance to the moon. And he knows also the radius of the moon. That was also measured, radius of the Earth, I'm sorry, that was also measured. Based on these relationships, he found the relationship of the two accelerations and the ratio of the two, the square actually of the two radii, or the radius of the Earth and the distance to the moon. From there, he deduced the universal law of gravitation. And from there, he said, okay, this is true for the Earth moon or the Earth apple. So it must be also true for any planet. Give me any planet and the sun. Before publishing his work, though, it took him a little bit more time to publish his work because he was struggling with one point, and that point is, where would I take the distance from the apple to the Earth? I mean, is it just 1 meter where it dropped from 1 meter or 2 meters? Or is it the entire radius of the Earth? Of course, he knew the answer. It has to be the entire radius of the Earth, but he didn't have a justification for it. Because why would I have to take the center? There are parts of the Earth that are on the other side. I mean, if the apple is in here, there are mountains on this side and mountains on the other side, and different places on the Earth. So why would I have to go all the way to the center? For that, he had to do calculus. He had to actually invent calculus to do that, to basically silence his critics. I mean, he didn't publish because he was afraid that there would be critics, because why would you do that? So he had his work in there. So he took that, and then he was able to explain the first law, the fact that by solving those equations, that the paths are elliptical. The second law, that the areas sweep equal areas, I mean, the planets sweep equal areas at equal times. And that has to do with the angular momentum, as I was saying before. That is derivable from this thing. And the last equation in here has to do with the conservation of energy, and that one. And that is the one that actually took a step further. That law, he used it, and we're going to use it for those sitting in Astronomy 125 for measuring the mass of Jupiter. He used it actually to find the mass of the sun. You can use it to find the mass of the sun. Obviously, for the case of Jupiter, you have to focus on the moons of Jupiter. We're going to track Io and find the mass of Jupiter using the same method that was used to find the mass of the sun, using any planet. It doesn't matter which. So this is, in a sense, the contribution of Mr. Newton. Of course, it goes a step beyond that. It can be used for other things also, like Halley's Comet and so on and so forth. Okay, so this is basically the entire unit. I know I started backward, and there was a reason for it, like I said, because we stopped at Mr. Copernicus last time, and Mr. Copernicus basically needed a supporter, and that supporter happened to be Mr. Galileo, who basically put all of these things together with his observations, and basically was able to support the work of Copernicus. Okay. For that, he got into trouble. Okay, so let me stop sharing this, and let me see if I can get one notes. I don't have my pencil in here. Actually, I do. I don't have the. Do I have a pencil? Maybe. Okay, I think we can do without it. Okay, because it's kind of a in here. So let me find first of all one note. And let me share it with you. Share. Okay, so I'm going to use the mouse. Hopefully the mouse will work fine. If not, I'm going to type in, okay? Draw. So this is basically what we're trying to, what the law says. It says p squared is equal to a cubed. This is the third law of Kepler, okay? For the case of the Earth, it's easy. Remember, P for the Earth is exactly 1 year. And we need P to be in years, not in any other number. Okay, I'm using the mouse, that's why it looks kind of, okay. For A, for the Earth, it's 1 astronomical units, exactly. Okay, so for the case of the Earth, I have 1 squared is equal to 1 cubed. Well, 1 squared, 1 times 1 is 1. For the a cubed, which is 1 times 1 times 1 3 times, that's 1 also. So this checks, okay? There is no question about it. For the Earth is no problem. Now we need to use the same thing to find the time it takes, for the example, for the case of the planet Mercury. For the planet Mercury, we need to find how long it takes Mercury in years, in Earth years, to go once around the sun. So what I say in this case, p squared is equal to the semi-major axis for Mercury. Remember, we found it to be 0.39. from last time. This is the table that we shared from Copernicus data, cubed. So all I have to do is cube this number, meaning I have to multiply this number 3 times by itself, 0.39 times 0.39 times 0.39. So I encourage you guys to do that while I'm doing this, okay? I'm gonna pull a calculator in here. And see what that number is. I know if you have a scientific calculator, you could do 0.39 to cube, but it's easy enough that we can do it this way. So 0.39 times 0.39 times 0.39. So the number is equal to 0.059319. Okay, technically, I don't really need to keep everything in here, but just to give you an idea, this is the number. This has to do with what is known as precision in this case, okay? 9, there is a 9 in here, I'm sorry. There is a 9 in here, okay? And 9 at the end, okay? So this is the number times itself 3 times, okay? But that's not what I want. I want P. I want the square root of this number. So I'll have to take 0.059319 under the square root. This should give me how long it takes for Mercury to go once around the sun in years, in Earth years, that is, okay? Obviously, it's gonna be less than a year. So let's do that, okay? So let's take the the square root. And it's giving me 0.24. 0.24 years, less than a quarter year. 0.25 is a quarter year. So quarter year is what, 3 months? So it should be less, slightly less than 3 months. If you wish, you take this number. So this is in years, by the way. So let me leave it as is first and multiply it by 12 to find how many months that is. So if I multiply it by 12 times 12, it's 2.9 months, not even 3 months to go once around. In other words, when the Earth goes when the Mercury goes 4 times around the sun, the Earth will go only once around the sun. Remember that idea of the conservation of angular momentum? The closer you are, the faster you move. That means 4 times Mercury will go once around the sun, whereas the Earth would have done 1 year exactly. Okay, so this is one thing. Of course, if you want to see how many days that is, you're going to multiply it by the number of days, and it's going to be 87.7 days. 87 Earth days, that is 87.7 Earth days. 24 hours, that is, okay? Roughly 87 days, okay? That's how long Mercury goes once. That's the year in Mercury is 87 days. Okay, about the summer. That's all. That's it. Okay. Now I want to do Venus also so that you see the comparison. I'm going to do at least 2 more from the other side of the Earth. Okay, the planets that are further away from Earth. Okay, Venus A is equal to 0.72 from last time. Let me make sure, okay? AU. Yeah, Venus is 0.72. This is what we found last time. Okay. So P squared is equal to A cubed. And A cubed again is 0.72 times 0.72 times 0.72. And remember, this will give you the square of the year, not exactly the year. Obviously, since this number is less than 1, when A cubed, it's going to be less than 1, definitely. So I'm going to do 0.72 in my calculator, and hopefully you guys are doing the same thing. 0.72 times 0.72. So it's giving me 0.37 something something, okay? 0.37. Again, I need to take the square root of this number. It's actually, I'm gonna 0.37 and some other numbers in here. So if I do that, that's gonna give me exactly how many years year in Venus is compared to the Earth. So if I take the square root of this number, it's 0.61 years, Earth years, that is. So it's not even quite a year, slightly more than half a year, but not quite a year in Earth. So I can write this same period in number of months. So all I have to do is just take the number and multiply it by 12. That should give me how many months that is. It's 7.3 months, 7 1/3 of a month. That's how long for Venus to go once around the sun. 7 1/3 of a month, 7 and 10 days, basically 7 months and 10 days for Venus to go once around the sun, and the Earth still did not do a full year. Still have what, 4 months and 20 days to complete the cycle. Okay, the Earth already we did it. So let me take another example. Just take Mars, for example. Mars, same thing. We're going to say p squared for Mars is equal to a cubed. We know a for Mars is 1.52. So 1.52 times 1.52. It's a little bit further than the Earth is. 1.52. So again, I'm going to cube, because this number is more than 1. So the year on Venus is going to be more than the year on the Earth. So let's take 1.52. and cube it, or multiply it 3 times by itself. That's the same thing. The answer is 3.511. So what I do in this case, I take the square root of this number, and the answer is going to give me how many years in Mars compared to the Earth years. So I'm going to take the square root of this number, and it's 1.87 year. In other words, the year in Mars is almost twice the year on Earth. How many months that is? Just multiply by 12 again. It's 22.5 or 22.48 to be more specific. Roughly months, not quite 24 months, but close enough, 22.5 months, just a month and a half, or 2 months and a half shy of, no, month and a half shy of 2 years. Okay, just to give you an idea. So let's take another object. I'm going to take an object that is far away. At least that's not part of the data that we have last time. And that is Neptune. This is the furthest planet. For Neptune, A is 30.1. So p squared is equal to a cubed. And that is 30.1 times 30.1 times 30.1. It's 30 astronomical units from the sun on average, okay? So that gives me p squared equals to, so I'm going to take 30.1 times 30.1 times 30.1 3 times. So the answer is going to be a big number. 30.1 times 30.1 times 30.1. The answer is 27,270. 27,270 and some change. Okay. So now P is just the square root of this number, 27,270. In other words, how many years on a Neptune, how many times Neptune goes around the sun when the Earth does that? So again, take the square root of this number, and it's 165 years. 165 years. When was Neptune discovered? Just to give you an idea. In 1846. 1846, 100 years later, it's 1946. So it barely went through a year from the time it was discovered up to this point. I mean, it's in its second year, barely started its second year from the time it was discovered. In other words, the planets that are very far, their year there takes a long, long, long time. This is not the longest year, by the way. If you take Pluto, which is a dwarf planet, you will find more than that. If you take Sedna, for example, it's even far more than that. And that is going to be part of your homework problem, by the way, for Sedna. Okay. So it's again the same formula that you're using. It obviously you can, if you know P for the case, for example, of Halley's Comet, you know P 76 years, you can find A. So in this case, you say A cubed for Halley's Comet is equal to P squared. You take 76 squared, and then you take its cubic root. For that, you really need a calculator, okay, to find it. But that's really the type of calculations that you're going to be carrying out in the next homework set. And I'm hoping that this really empower you to help you understand the material better. Sounds good? Thank you. Thank you, guys.
Yeah.
Very good. Thank you. So I'm going to stop the recording right now. Do you guys have any questions? Okay, I'm going to stop the recording and I'm going to see you guys next week. Okay.